is the project scientist for SOFIA, and she's here to give you an overview of what SOFIA does and how it views the universe in the infrared region. So keeping it short and to the point, not reflective of her stance, but to move things along, please give a warm welcome to Dr. Pamela Marcum.
Thank you very much, David, for that excellent introduction to our center and to SOFIA. And it is a real privilege to be able to talk to you today about SOFIA. And oh my gosh, you're going to get to see it later. So how cool is that? Let me go find my clicker, which I placed over here. Hopefully it's still here. We're in good shape so far. All right, as it was mentioned, I am the project scientist for SOFIA, but SOFIA has a very large team of scientists and engineers and all the infrastructure that goes with that. I'm not going to be talking too much about that. What my talk is going to be focusing on mostly is just why we have SOFIA, why it's able to do the science it's able to do, and also an introduction as to why we care about infrared astronomy. So hopefully by the end of my talk you'll have a good sense of what infrared astronomy is all about and why it's a really important part of the electromagnetic spectrum, which you can actually see over here on the side. So you might want to take a quick look at that as we go through the talk to kind of orient yourself as to what wavelengths we're talking about. So on here, we're basically talking about the wavelengths that would be redward of the rainbow. And I'll be talking more about that in my slide too. And I would ask that David pull me off stage when the bus arrives, because I do tend to go long if given an open amount of time here. Okay, so SOFIA is a 747. It was dramatically modified. As you see, most 747s don't have a hole in the back. So this 2.7 meter telescope was placed in there, and the 2.7 meter telescope was provided to us by our German partners. SOFIA is an international collaboration between the US, NASA, and Germany through their space agency, DLR. This is a picture of one of the test flights of SOFIA. As you might imagine, when you modify so drastically a jet plane, you really do have to put it through a lot of rigorous tests before you can ensure people can safely fly on it. Fortunately, it passed those tests with flying colors. Let's see, so I can talk more about that, but I will proceed. This is an interior view of the plane, and I just very quickly want to highlight a couple of things. It looks just like a professional observatory. For anyone who's ever been to Kitt Peak or Hawaii, or seen the interior of an observatory. If you haven't, don't worry. I'll show you some pictures of astronomers in action here in a minute. But the main thing I wanted to point out is, well, the astronomers are working here on their consoles, and there's some flight operations, mission operations people as well. We also have a place set aside specifically for teachers and people from museums and reporters to be on board. They actually are integrated in the research team, and once the plane is flying and taking data, people can mingle back here and kind of look over the shoulder and actually get involved in the excitement of data collection. Right here is where the science instrument itself is located, and right here in an open cavity, well, there's sort of like a big garage door that closes when the plane takes off, but once it's up at altitude, that garage door opens, the cavity door opens, and exposes that telescope completely to the atmosphere. So you might think, how on earth can a telescope stay stable enough to actually see, to take data on an object? But that's a testimony to how incredible the engineering of this plane is. The aerodynamics are amazing over that hole. This, of course, is a pressurized bulkhead. Very important if you want to be able to survive on this side of the plane. Okay, so this is a quick look at how the telescope itself works. Down here is that big 2.7 primary mirror. It's basically a light bucket. Up here is another tiny little mirror that helps bounce the focus light back down so that it can be channeled into the instruments. So this is some source that you're looking at, a star, a nebula, whatever. And there's an interesting third mirror, it's called the tertiary mirror here, that is specially made to separate out the infrared light from the visible light. And you're going to see how that actually works in a moment. And of course, over here, on the other side of this light tube, is where the science instrument itself is located, and you're going to see down here is where our visible light guider is located. So that guiding camera helps us stay locked onto position, along with several other components like gyros that also help us stay locked onto position when we're observing. Okay, so let me just start the animation real quick. So what you're going to see is light coming from that source, bouncing off the mirror, bouncing off the secondary in a focused orientation. And then you're going to see the separation of the light, the infrared light, and then the visible light. So let's start the motion right now. So the light comes down, it bounces off the primary, it's focused, it comes off the secondary, the infrared component of that beam ends up going through this light tube into the infrared science instrument, and then the visible light passes through that first filter and bounces off the second mirror and ends up in our tracking camera. So this is the way that light is collected. I might also mention, this is where that big pressurized bulkhead is located. So this is the interior side where the people work. There is this tremendously large metallic spherical bearing upon which the 17-ton telescope assembly rests. And it floats on this really thin film of oil, and basically a series of springs help keep it isolated from the jiggling and wobbling that you might imagine you would encounter on the plane. So this thing is incredible in action. As you're taking data, and as the plane is experiencing a little bit of turbulence, which it doesn't do very often because we do fly in the stratosphere, you'll see on the back side of where the counterweight is located, on this side, I have a picture. Look, maybe I should just go there. So here's an interior shot. So this counterweight helps balance the telescope, which is on the other side of the bulkhead. And this thing looks like it's going like this, and it's doing all this motion in flight, but it's really not moving at all. It's the plane that's moving around the telescope. The telescope is just locked in, fixed on target. So it's really an incredible engineering feat, not to mention the astronomical significance and worth. Okay, so what you see here is an instrument. It's the GREAT instrument, G-R-E-A-T. It stands for something which I can't recall right now, but it is a heterodyne far infrared spectrometer created by our German colleagues. And so they're getting ready to install it. Here is the back end of that light tube that actually passes through that spherical bearing that holds the telescope. And of course you see the pressurized bulkhead here. So enough about that. Let's go to the next slide. This is what a professional observatory looks like. You see a lot of computer monitors. These guys are working. These are the scientists actually who are watching the data coming in. Here is the PI of the instrument that happens to be mounted on the back there. It's called Forecast, developed at Cornell University. And then we have the telescope operator, and then you can't even see, there's some seats up here in the front, in the foreground, that are making sure the airplane is staying on its path, and so on. Okay, so speaking of the plane staying on path, let's take a look at how that works. What I'm going to show here is actually a map, a real map that was actually followed for one of our flights of the track that the plane took. Overlaid on a map. And you'll see all of these legs, these jots. So what's going on there? Every leg represents a single object that it's looking at. And then when it needs to get back on another target, the plane itself typically has to change direction, and then it follows that path for a while until another target needs to be looked at. If you could magnify the map, blow it up a little bit, what you would notice is that these tracks are actually curved. Well, what's going on there? Well, the telescope is basically an out-as telescope. And what that means is that it can track the curved paths of celestial objects in the sky by moving, so this is the telescope tube, it can move this way, and typically a ground-based out-as telescope can also move this way. And by a combination of this motion and this motion, you're able to track along the sky. You'll see that this is just star trails. You take it to, oops, I didn't mean to do that. You open up a camera and let it expose for a little while, and you'll see that the stars move in circles around the sky, around the pole, right? That's the North Pole right there. And so you've got to keep up with that motion. Well, I shouldn't say unfortunately, we got it all fixed, right? SOFIA can only move in this direction. So how does it move in this direction? The plane itself. The plane itself moves in that direction. That's why these paths are curved, so that the combination of this motion and this motion allows you to actually track a star, or a nebula, or a galaxy. So it's pretty incredible, actually. The amount of work that actually goes into figuring all that out to be able to tell the pilots which way to fly. How am I doing on time?
You're doing fine.
All right, so we talked about kind of what SOFIA does, but what are the advantages of using SOFIA over, say, a ground-based facility or space-based facility? There's advantages that SOFIA has over both of those. Well, first of all, let's just talk about, really quickly, SOFIA's predecessor was the KAO. And why aren't we still flying the KAO? Well, it had a much smaller mirror. It was 1 meter rather than a 3-meter class telescope. And the advantage that comes with a larger mirror, the kind that SOFIA has, which is about as big as you could fit into the plane, is that a larger mirror gives you better resolution. It's blurrier with a smaller mirror than a larger mirror. Another advantage that SOFIA has over a ground-based facility is that large swaths of wavelength are completely blocked out from a ground-based observatory. Even something stuck way up high, like Mauna Kea in Hawaii. Everywhere you see blue here is those wavelengths are blocked out from the ground. And a similar shot of what the transparency of the Earth's atmosphere looks like is from SOFIA is right here. Yeah, there's still some areas that are somewhat blocked out, but they're not completely blocked out. And basically the entire wavelength range, from optical all the way out to sub-millimeter, are available to SOFIA. All you need is the instrument to put on the back, and you can collect data at those wavelengths. So that's a huge advantage. You might say, well, you know, if you go to space, you get rid of all the blue, right? Yes, you do. The disadvantage of going all the way to space is you can't come home every night and replace your instruments, fix things that are broken, and so on and so forth. So it's a balance between putting up with a little bit of leftover opacity in the atmosphere versus the tremendous flexibility of being able to service your observatory like a ground-based observatory on a regular basis. All right, so stratosphere is part of SOFIA's name. Here's a really cool shot of kind of where the stratosphere begins and where the troposphere begins. The tropopause is what separates it. And why we care about flying in the stratosphere is because it's above 99.5% of the total water vapor in the atmosphere. Water is really bad for infrared astronomy because the water molecules themselves tend to absorb the energy from infrared photons. They absorb it and then they wiggle, they jiggle and they rotate. And then because of that process, the infrared photons that would be coming from space don't actually make it all the way to the ground, as I showed before. And so if you fly up high, then you're in a drier area and you're actually able to catch those photons before they get absorbed by the water. One other reason we like the stratosphere is because it's a layer that's called an inversion layer. If you see here, this is temperature. Colder is on the left-hand side, warmer is on the right-hand side. As we know, as you go up higher and higher and higher, it gets colder, colder, colder. We know that for those of you who go hiking in the mountains, it gets colder as you go up. But then, the curious thing about the stratosphere is that once you enter the stratosphere, it starts getting warmer, warmer, warmer as you go up, up, up. Why is that a good thing? All the cold air is already on the bottom in the stratospheric layer. So you don't have a lot of turbulence. You don't have cold air trying to come down. It's already down. And it gives you a nice, smooth ride. Except for the occasional thunderheads. Okay, as I already talked about this, the advantages of being able to service it every day. One other great thing about SOFIA, I've already mentioned, is that it covers a wide swath of wavelength, and it's going to live for a long time. It has a 20-year baseline. All right, so let me just real quick get to infrared radiation. And I'm just going to get to the punchline here because I think your bus is ready to take you on. As we know, light, radiation, is made up of a large swath of different wavelengths. We only see with our eye a very small portion of what's really out there. A rainbow is a perfect example of the spectrum of visible light. Infrared, of course, is what Sophia's interested in, and that would be light that has a wavelength of about the width of a hair. The reason we care about infrared is that it can map temperature changes, and this is a great illustration, visible versus infrared, where you see the intensity, the higher intensity is where areas where, the warm blood is a little bit closer to the air and it's able to radiate that heat in the form of infrared. Of course, the lizard is cold-blooded, so it shows up as a dark area against the hand that is warm. Just like with terrestrial infrared thermal cameras, astronomy makes use of those temperature differences as well. This is a picture of the Horsehead Nebula. This is a visible, and basically you see mostly just a dark area of clouds and dust. The near-infrared allows you to peer through the dust to actually be able to see the stars. So infrared doesn't like to go through water, but it can go through dust very easily. It zips right through it. And that's a great thing because it allows you to see right to the heart of a dusty core where star formation is occurring. Mid-infrared, a little bit longer wavelength, actually maps out the warm dust itself. So by looking at just these three wavelength ranges, you can tell a lot about what is going on in the star formation region of this part of our galaxy. Infrared also contains a rich set of molecular features which allow us to do chemistry deep down inside of an otherwise obscured star-forming region. And that is my last slide. So what have we learned today? We've learned that, unlike visible light, infrared's able to zip right through the dust. It doesn't zip right through water molecules. It gets absorbed. That's why we need to fly SOFIA, because it's above most of the water. And infrared observations allow you to pick out the warm from the cold. So it's very useful to look at warm cores of star-forming regions. If you'd like to learn a lot more than I've been able to tell you, feel free to log in and check out our SOFIA webpage. And I'm happy to entertain any questions that you'd like to email me as well. So that's my contact information. You will be hearing more about SOFIA science from the Deputy Project Scientist, Dr. Tom Rolig, later today. So you haven't heard the end of SOFIA yet. There's plenty more to come. Thank you.